Hey YouTube family, Namaste. I hope that all of you are very fine. This is Shubhradev Nath and I welcome all of you to my channel Bengal Bro Tutorial. Welcome to the third lecture of the chapter Electric Charges and Field. In the last two lectures, we have discussed all about charge. And in this lecture, we will solve some amazing questions based on charge. Actually, I have selected all these questions from different set of books so that if you solve them, you can get a strong foothold with the concept as well. So without any further delay, let's start today's session with question number 1. The charge on a proton is plus 1.6 into 10 to the power minus 19 coulomb. And that on an electron is minus 1.6 into 10 to the power minus 19 coulomb. Does it mean that the electron has a charge of 3.2 into 10 to the power minus 19 coulomb less than the charge of a proton? See, mathematically, plus 1.6 into 10 to the power minus 19 coulomb is a number which is greater than minus 1.6 into 10 to the power minus 19 coulomb by a difference of 3.2 into 10 to the power minus 19 coulomb. But in the representation of a charge, we cannot look with the mathematical view. Since the magnitude of charge on a proton and that on an electron is same, it means that an electron and proton both has the same amount of charge. The positive and the negative sign only denotes their opposite nature, which means they have completely opposite behavior. So we can write that no, both proton and electron have same amount of charge. The positive and negative signs just denotes their opposite nature. Okay. Now let's see question number 2. What does the equation Q1 plus Q2 equal to 0 signify in electrostatics? According to the property of additivity of charge, the total charge of a system is equal to the algebraic sum of the charges of the individual system, taking into account their size. Now, if you look at the equation, obviously we can understand that the system is constituted of two charges Q1 and Q2 such that their algebraic sum is equal to 0. Now, this is only possible if Q1 and Q2 have same magnitude of charge with opposite sign. For example, say Q1 and Q2 is equal to Q. Okay, but Q1 is equal to plus Q and Q2 is equal to minus Q, which means that their magnitude is equal but their charge signs are different. Then if you add Q1 plus Q2, the answer will be plus Q plus of minus Q, which is equal to Q minus Q, which is equal to 0. So the equation implies that the charges Q1 and Q2 are equal and opposite. The equation Q1 plus Q2 equal to 0 signifies that charges Q1 and Q2 are equal and opposite. So let's move to the next set of questions. Question number 3. Calculate the charge carried by 12.5 into 10 to the power 8 electrons. In this question, we have to find the total charge which is carried by this number of electrons. Here we will use the property of charge called quantization. So, according to quantization of charge, the total charge Q is equal to number of electrons into charge on one electron. Here N means number of electrons is 12.5 into 10 to the power 8. And E is equal to 1.6 into 10 to the power minus 19 coulomb. Therefore, we can calculate the charge carried by this number of electron using this formula, which will be equal to 12.5 into 10 to the power 8 into 1.6 into 10 to the power minus 19 coulomb. 10 to the power 8 into 10 to the power minus 19. If you multiply, you will get 10 to the power minus 11. And 12.5 into 1.6 will be equal to 20. So the final answer will be equal to 2 into 10 to the power minus 10 electrons. Question number 4. Can a body have a charge of 0.8 into 10 to the power minus 19 coulomb? See, such a charge can only exist if it is an integral multiple of E. So, in this question we have to check whether we can express it in the form NE, where N is an integer. If it is possible, then only the existence of charge equal to 0.8 into 10 to the power minus 19 coulomb is possible. So let's solve and see. The charge on a body is always an integral multiple of E. Therefore, 0.8 into 10 to the power minus 19 coulomb is equal to some integer multiplied by 1.6 into 10 to the power minus 19. From here we can calculate N is equal to 0.8 into 10 to the power minus 19 by 1.6 into 10 to the power minus 19. We can cut this, and 0.8 by 1.6 is equal to half, which is equal to 0.5. Obviously, this is not an integer, which means that such a charge is not possible. Hence, we can write that since N not equal to integer, a body cannot have a charge of 0.8 into 10 to the power minus 19 coulomb. So let's move to the next set of questions. Question number 5a. How many electrons make 1 coulomb of charge? Here the total charge is given to us and we have to calculate the number of electrons that is present that will make 1 coulomb of charge. So again we will use the property of charge called quantization. We have Q is equal to Ne. Here Q is equal to 1 coulomb, means the total charge, and charge on 1 electron is equal to 1.6 into 10 to the power minus 19 coulomb. Alright. Here we can write that N is equal to Q by E. Therefore, N is equal to 1 by 1.6 into 10 to the power minus 19, which will be equal to 6.25 into 10 to the power 18 electrons. Thus, this number of electrons will constitute 1 coulomb of charge. Moving to the second part of the question, if a body gives out 10 to the power 9 electrons every second, how much time is required to get a total charge of 1 coulomb from it? Means that there is a body from which 10 to the power 9 electrons are ejecting per second. So we have to calculate after how much time the total charge carried by the electrons ejected will become equal to 1 coulomb. We can easily solve this question using the unitary method. See, from the first part of the question, we have calculated that 6.25 into 10 to the power 18 electrons constitute 1 coulomb of charge. Okay. That means here we have to calculate how much time will be taken for the body to eject 6.25 into 10 to the power 18 electrons. So let's begin in this way, that 6.25 into 10 to the power 18 electrons constitute 1 coulomb of charge. Now 10 to the power 9 electrons are being given out by the body in 1 second. Therefore, 1 electron will be given out by the body in 1 by 10 to the power 9 second. Therefore, 6.25 into 10 to the power 18 electrons will be given out by the body in 1 by 10 to the power 9 into 6.25 into 10 to the power 18 second. Now if you divide it by 60, it will get converted into minute, and then again if you divide it by 60, it is going to get converted into hour, divided by 24, and then 365. So the whole value gets converted into years. And if you solve this, you will get a value somewhat near about 198 years. This is the answer. That means the body will take about 198 years to eject electrons, which will constitute 1 coulomb of charge. So let's move to the next set of questions. Question number 6. A polythene piece rubbed with wool is found to have a negative charge of 3 into 10 to the power minus 7 coulomb. Part A. Estimate the number of electrons transferred from which to which. So we have a polythene piece that has been rubbed with wool, due to which it has acquired a negative charge of 3 into 10 to the power minus 7 coulomb. Okay, so it means that electrons have been transferred from wool to polythene piece, and that is why it has acquired a negative charge. So this much everyone understood. Now we have to calculate, using the property of quantization of charge, the number of electrons that have been transferred. We have Q is equal to NE. It implies that N is equal to Q by E. Here Q is equal to 3 into 10 to the power minus 7 coulomb, and charge on one electron is equal to 1.6 into 10 to the power minus 19 coulomb. Therefore, number of electrons transferred will be equal to 3 into 10 to the power minus 7 by 1.6 into 10 to the power minus 19. If you solve this, you will get the answer equal to 2 into 10 to the power 12 electrons. And finally, you can conclude this answer by saying that since polythene acquires a negative charge it means that electrons have been transferred from wool to polythene. Now let's see the second part of the question. Is there a transfer of mass from wool to polythene? Obviously, there will be a transfer of mass because electrons have a finite mass, which is equal to 9.1 into 10 to the power minus 31 kg. So let's calculate the mass that has been transferred from wool to polythene. Mass of one electron is equal to 9.1 into 10 to the power minus 31 kg. Therefore, mass transferred will be equal to the number of electrons transferred into mass of one electron. Now, number of electrons transferred is equal to 2 into 10 to the power 12, and mass of one electron is equal to 9.1 into 10 to the power minus 31 kg. Now, if you solve this, you will get 1.82 into 10 to the power minus 18 kg. Which means that this much amount of mass has been transferred from wool to polythene. And obviously, you can see that the mass transferred is very, very small, to the power of 10 to the power, to the power of minus 18. Now we can move to the next set of questions. Question number 7. When a glass rod is wrapped with silk cloth, charges appear on both. A similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with law of conservation of charge. According to the law of conservation of charge, the total charge of an isolated system, okay, it remains unchanged with time. But here, if we see that the glass rod and silk cloth, which were initially neutral, have acquired charge after they were rubbed with each other. Now, how can we explain this observation with law of conservation of charge? So, the total charge initially was 0. The total charge of the glass rod and the silk cloth initially was 0 because they were both neutral. Now we have learned that when two bodies are rubbed with each other, then they acquire charges of equal magnitude but of opposite nature. It is observed that when glass rod is rubbed with silk cloth, the glass rod acquires a positive charge and the silk cloth acquires a negative charge. And the magnitude of charge developed on both the bodies will be equal. So now, after rubbing, if you calculate the total charge of these two bodies, then again the answer will be equal to 0 because they will have charges of equal magnitude with opposite signs. Finally, we can say that the total charge has remained unchanged with time. In this way, we can explain this observation with the law of conservation of charge. Actually, I am not writing a formal answer because that you can get in the lecture note, okay, which will be given in the description box. If for now, if you have understood, then it's okay. Question number 8. Ordinary rubber is an insulator, but the special tires of aircrafts are made slightly conducting. Why? Unlike the normal tires of vehicles which are made up of rubber, the tires of aircrafts are made of special kinds of rubber that are actually slightly conducting. Now this is done so that the charges acquired by the tire due to friction between the tires of aircrafts and the road during landing can get transferred to the ground. If they are made up of ordinary rubber, then what will happen? The charges will get accumulated and which can result in electrical spark and then cause fire. And that will be very dangerous. That's why the tires have to be made slightly conducting so that the charges can easily flow to the ground. So let's move to the next set of questions. Question number 9. Vehicles carrying inflammable materials usually have metallic ropes touching the ground during motion. Why? Inflammable materials means those materials that can catch fire very quickly, like petrol and diesel. And you can answer this question using the concept that we have used for the previous question only. Actually, moving vehicles, they become charged due to friction with the air as well as with the road. So, if we don't transfer this charge, then the charges can get accumulated and can cause accidental fire. That's why such vehicles, they have metallic ropes touching the ground in order to transfer the charge developed to the ground and prevent any sort of accidental fire. Question number 10. An ebonite rod held in hand can be charged by rubbing with flannel, but a copper rod cannot be charged like this. Why? Can you answer this by yourself? Think an answer. Then come to the video and see whether your answer is matching with the original answer or not. The ebonite rod being an insulator, so when it is rubbed with flannel, the charge stays in that very place where it has appeared. But copper rod being a metal will transfer the charge to the ground through our body, and that's why charge will not stay on the copper rod, or we cannot charge a copper rod by rubbing it with a flannel. Okay, so now let's move to the next set of questions. Question number 11a. Can two bodies having like charges attract each other? See, this is a very important question because from here you can learn a new concept. According to the fundamental law of electrostatics, like charges repel each other. But in the question it is asked that can like charges attract each other? Now this is a contradicting situation. Yes, two like charges can attract each other if and only if the charge on one body is much more compared to the charge on the other body. For example, let us consider two bodies that are positively charged. Okay. Now, when these two bodies will be brought closer to each other, then this positive charge will repel the positive charge on the other body due to induction. And this positive charge, now they will move to the other end. So you can see there is a temporary electrification developed in this body. One side of the region of this body has become negatively charged and the opposite side has become positively charged. So this side will get attracted and the other side will get repelled. But the force of repulsion will be less compared to the force of attraction and the two bodies will get attracted towards each other. So two bodies having like charges can attract each other only and only if the charge on one body is much greater compared to the charge on the other body. Now B. Can a charged body attract an uncharged body? Yes, a charged body can be attracted towards an uncharged body by the process of induction only. See, we have a charged body and another, let us consider another body that is uncharged, means which is neutral. Now, when the charged body will be brought closer to the neutral body, then the positive charge in this body will repel the positive charge of this body. So they will move to the other side of the body and will develop a temporary electrification. So now this body has two regions. One half is negatively charged and the other half is positively charged. But still the overall charge in the body is still neutral only. Okay, so this region will get attracted and the other region will get repelled. But the force of attraction will be more compared to the force of repulsion and eventually the two bodies will get attracted towards each other. Okay. Question number 12. A comb run through one's dry hair attracts small bits of paper. Why? What happens if the hair is wet or if it is a rainy day? Actually, when we perform the magic trick of combing the hair with a comb and then bringing the comb near bits of paper which gets eventually attracted, we always prefer dry hair. It is because in that case the friction will be more and charges developed will also be more. Now the small bits of paper that are neutral get attracted. How? Again, by the process of induction. If the hair is wet or if it is a rainy day, then the charges developed will be very less because in this case friction will be less and that will not be enough to attract small bits of paper. So on rainy day or when the hair is wet, the small bits of paper will not get attracted to the comb. Okay, so let's move to the next set of questions. In question number 14, we have two conducting spheres X and Z that are made to stand on insulating stand with a cylindrical conductor Y in between them, and the three are electrically connected. A negatively charged ebonite rod is brought close to them. Now question number A. What will be the charges on X, Y and Z? Now, when this ebonite rod will be brought close to this system, then the negative charge will also repel the electrons on X. So, the electrons will move from this region to Z. The electrons here will move from X to Z, and this side will become positively charged. So, when this ebonite rod will be brought close to this system, X will develop a positive charge, Z will develop a negative charge, and Y will remain neutral. Now, if the conductor is earth for a moment, means when the conductor Z will be connected to the earth, then the negative charge will flow to the ground. Okay, so what will happen after that? When the ebonite rod will be moved, this positive charge will evenly spread to all the three bodies, because we know that the positive charge, it actually distributes itself over the conductor. That's why after the removal of ebonite rod, the positive charge will evenly spread to the three bodies. Now question number C. In the presence of ebonite rod, conductors Y and Z are removed. What is the charge on each of them? So when this ebonite rod will be brought close to this system, then the electrons will actually move to Z, and this X will become positively charged. So when you will remove Z, okay, so when Z is removed, then some more electrons will actually travel to Y, and Z will be negatively charged. Now Y is negatively charged and X is positively charged, and more positive charge will develop on X. Then again when you will remove Y, then what will happen? X will remain positive charge as usual. Understood? So in the presence of ebonite rod, when Z is removed, Z will become negative charge. And when Z is removed, then more electrons will flow to Y, and then Y will also become positive charge. And when Y is removed, the X will remain positively charged only. Question number D. The ebonite rod is made to touch X. What are the charges on X, Y and Z? Till now, we were charging this system by the method called induction. But when the ebonite rod will be made to touch with X, then X will get charged by the process of conduction, because these three are conductors, and the ebonite rod will share its charge with X. So since it is negative charge, so when it is made to touch with X, some negative charge will flow to X. Alright, and some charge will also flow to Y, and some charge will flow to Z, and all the three bodies will become negatively charged. So let's move to the next set of questions. Question number 14. Two charged copper spheres A and B have charges QA and QB. So we have two charged copper spheres A and B. Charge on A is QA and charge on B is QB. A third sphere C of the same size but uncharged is brought in contact with the first and then in contact with the second and finally removed. What are the new charges on A and B? So we have another charge having same size but it is uncharged. Now when C will be brought in contact with A, then the total charge of both the spheres will get equally distributed to each other, because we have learned this when we were actually discussing about the method of charging by conduction, that when two conducting bodies of same size, okay, when they are brought in contact, then their charges get equally distributed. So when A will be brought in contact with C, then the new charge on A, that is QA prime, and on C will be equal to QA plus 0 by 2. QA is the charge on sphere A and 0 is the charge on sphere C, which will be equal to QA by 2. Now, when the sphere which is having a charge of QA by 2, the sphere C, is brought in contact with B, then again the total charge of sphere C and sphere B will get equally distributed. So, after the charged sphere C is brought in contact with B, new charge on B, that is QB prime, will be equal to charge on B, which is QB, plus charge on C, which is QA by 2 by 2. So it will be equal to, if you take LCM, then 2 QB plus QA by 2. So the answer will be QA plus 2 QB by 4. This will be the final answer. So that's all for today. Hoping to see you very soon in another video. Till then, take care of yourself, keep studying for your exam, and have a wonderful day ahead. Goodbye.